Hello and welcome to the fourth video in lesson 3, where we'll be talking about costs in Leap. In this video, we are going to talk about costs, how to enable costs in Leaps, the different methods of functions there are for using or putting in costs, how to do cost in different sections, so cost difference between transformations, resources and demand, how we're going to cost effects, so we can cost externalities because that's done a little differently on the input side, and then look at the cost results. And of course, costs is the first things policymakers are going to ask about when you're saying you have a different scenario. How much does it cost? So it is quite important for that effect, but it is also even more important when we're talking about optimization later on, because then we usually optimize for least cost scenarios. So that's what we are doing. So to enable costs in Leap, we will have to go to our settings window and in scope and scale as per usual. And we'll just have to apply costs. It's quite easy. And then we will have costs in all of our different aspects of the model. So as long as that is tagged on, then we can do costing, just for good measures. Now on a branch level, we also have to input our costs, and that we can do like this. Here I've chosen in my industrial sector with my heating for my iron and steel. I have activity levels, final energy intensity, and all these different variables we know. We also here have the demand cost. So here we can say that we are on the technology level. So that's where we do our costing in this. And the expressions are more or less all the same as they are in every other place. This functions quite a lot like final energy intensity, as is it is a unit, in this case some kind of money, that could be in any currency you want. And then per the activity, in this case per metric ton. So that's our activity level. So the metric ton is how we define our activity level, and that's also how we define our cost, that is the per activity level. And you can see here we have a different method of costing here that we can choose in our current account scenario that we will go into. So before we do that though, I want to talk quite quickly about absolute versus relative cost. Well, the absolute cost in the system is if you put an absolute money value on something. So that means that this phone is $100 I don't know, and that is the base price that you would pay either as a society or as a consumer. But the relative cost, that is the cost deviation from your other scenario. So for instance, if I had another phone here, which I don't, then I could compare the two phones and say one is $100 and one is $200, then the cost of that, the relative cost between them is, for the scenario I want to buy in the shop, is $100 between them. So that is the difference between the absolute cost and the relative costs. When you are doing absolute costs, your final results are when you have all your costs, it would look like a bit like a state budget, like how much money did the country of X, Fredonia, use on coal, on natural gas for our urban heating sector, and so on and so forth. While in the relative, it would only be how much more money in the mitigation scenario was spent on renewables compared to the baseline scenario. The big difference here is that you only need then to input cost in for one scenario maybe, and two, you only need to input cost where there is a difference. So in all inherited branches on inherited expressions, you don't really need cost because the cost difference is 0. So if you have just the same amount of energy efficiency for your urban households in your baseline versus your green or wind turbine scenario, let's say that, if there's no difference between these two, then you don't have to actually apply cost. You only need to apply cost where there is a difference, where it matters. And that also means that the relative cost is much easier to work with, because you only need to input a lot less data. Usually what we do is we don't put in cost in our baseline scenario, because that is what it is in many ways. If we are doing business as usual, we will have business as usual cost, probably, and then we can see instead we have the cost difference in our scenario where we do change things. So that is where we are looking at. The only big difference I can tell is if we have the same cost for something like importing a resource. So if you're importing coal and it has a fixed cost, we can apply that to all sectors. And then if you import less coal, we will have a cost savings measure. So we need to input that as well. If that was 0 in our baseline and it was non-zero in our mitigation scenario or low coal scenario, then we will still have spent more money in our low coal scenario, just because we have data in our low coal scenario that we don't have in our baseline scenario, which of course is not realistic. The same thing goes for optimization. Any place you want to optimize, you need cost if you want to do least cost optimization, which you usually will. So there you have to have cost on everywhere you need to, but that may not be between scenarios. It just has to be in the scenario, even if there's no differences. Otherwise the model cannot optimize for that. At least optimizing something that's free is not an optimization, it's just good in terms of the math in the optimization. So we have just like we have different forms of having our energy, we have different forms of applying our costs. So we will go through those. And these are quite different than in any other sector, because they have been specifically meant for cost independently on what type of, almost independently, independently on which type of energy method you're using, or energy analysis method you use. The only one that's really big difference is this cost per device sold. That is only when you have stock turnover that this is relevant, because that's the only place where you are really looking at a sold device or sales that is in a stock turnover method. Otherwise, the activity cost, that's just same as energy intensity. We just put the cost per some activity, which is usually the energy use. So that is also good for something like both in terms of some places in demand, but also quite a lot when you're talking about consumption and also the resource price, the price of a gasoline. That's usually done by activity. Because it's a cost per liter of consumed gasoline, for instance. So that's how we do that. And then these costs of the different ones, cost of energy and total cost, are usually applied a little differently. So cost of saved energy, or CSE, that usually relate to energy efficiency measures. It doesn't have to, but that's usually where it's practical, because then you're actually applying a cost on your energy savings, which is something that usually occurs in terms of investment costs for energy efficiency measures. And total cost is just a blanket cost. It costs this much per year. So that is independent from the consumption. So that's pretty special, but there is a reason for that, and we use that usually with annualized costs, but we will get into that. So here we have the cost function. It is the quite simple one. So for instance, here we are talking about, we can see we have our activity level up here that we know and love, so to speak. and we have input a bunch of data for that. And of course, we have here specified a number of households, and then in our branches in that, it becomes a percent of household in shares and saturations and so on. So then we apply those numbers. When we are doing the same thing with these places down here where we have our technologies, these are the only ones that are techs. And that's where we put our cost. So we can see that these are based on households. These are the unit of households because it just inherited the units from the branch called households, but the unit was specified there. We can see that our cost becomes dollars per household, and that's the activity in this case. So that means it might not actually be dependent on the energy consumption. It usually isn't. It's dependent on the production, consumption, share of square meters and so on, and that has a certain cost. You can of course also have that as a cost per energy, but actually you cannot have that for the current year because with the linear model we don't have we do not have results before we can have input. So if you do that, you will only get the cost per energy for the previous year. So usually you have that as on your input, just on your input side. So that's what we do with the activity cost, the simplest method and the one that is generally most widely used. Then we have the cost per device sold. This is only really applicable for places where we have stock turnover. Yes. So that's pretty important. It also it specifies the cost per unit, which is quite nice because then you can define the cost. If you do use relative cost, you could say how much is the cost of an electric car compared to a ICE normal car, or how much is the cost of a very energy efficient fridge more than the non-efficient fridge. And since it is cost per unit, it means it is also the only sales cost. It does not relate to the energy cost at all, but none of these do that anyway, because the energy cost we define somewhere else, and I will show you. So this is just the sales cost, which also means it does not include general O&M, which is a bit of a shame, but that is how it is if you use this method. But also that it is pretty similar to the activity cost, but in this case the activity that we're generally using is the sales, and then that's going on per year. But of course fuels are not included in any of these costs, but we'll get to how to do that later. Then we have the cost function called the cost of saved energy. If you imply that in your current account, you will get a little the little window up here, where it will ask you to say specify your units, how much is your cost of electricity saved versus another scenario. So if you do that, you can only apply that in a projection scenario, not in current accounts, because you have to compare it to another scenario. But what does this mean? Well, it does mean that it finds out the differences between the energy intensity between two scenarios. If you look at the formula, so we have the energy intensity for your baseline and your energy intensity for your chosen scenario, and then what is the difference between that, and then we have a cost that's done on that, multiplied by the activity level to see how much general energy are we expecting to save here. And then the CSE, that's the cost of saved energy that you specify. Why do we do that? Because this is a bit of a weird formula, because then the more energy that we save, the more it will cost us. But of course, remember here that fuel costs are not included in these costs in the demand side, because we do that elsewhere. Then this is the cost for applying an energy saving measure. So usually that occurs for instance, in industries or in households where we're doing specific policies for energy efficiency. This could be, quite clearly, it could be the added insulation in houses that has a cost, but it also makes you save energy. But then how much cost per energy saved or energy intensity that difference that will create, that is what we then put into this. So it's very good for finding the cost of EE measures. Then here we have total cost. It is just the total cost per year. So we can just say, hey, in no matter anything else, our cost in 2020 will be this, will be a certain number, while in 2040 it will be a certain other number. And we can just put in no matter what happens in terms of energy. That is also pretty good for maybe inputting other indicators. For instance, the total cost of let's say having rapid chargers in a system, that setting those up might incur a special cost, but it has nothing to do with a specific number of electric cars, because we can adjust that independently. Or we have some kind of a measure that is just we just have to invest in that no matter, and it will occur a cost no matter how much it's used. So if you had a power plant that we want to make, well, it is going to cost a number of billions of dollars to make and have this power plant, no matter how much energy is being produced. So you can use that as a total cost, and then of course incur the cost of fuel elsewhere and the profits of producing fuel elsewhere as well. So that can also be, you can also incur quite a lot of complicated costs on the side, maybe like in Excel, and then apply that into a total cost function into Leap, which also means it's quite good for incurring O&M cost as well. But it is independent, and that is maybe a little interesting, but it's really good for large scale investments. So if you are doing the investments like a plant or a new industrial plant or urbanization, if you have differences in increase in urbanization in your scenarios, well, there will be a cost incurred in building all these houses, but it will be independent from how much energy they're using or how many people living with them, which can also be practical. So now I'm just going to talk about a annualized cost function. So that is the important part here, is that this is a function, not a method, which means it is something that you write in your Leap expressions. What this is basically similar to present time value in Excel and other places, where you annualize your capital investments over your lifetime and then occur that. If you're doing that on the energy side, which this isn't, it would be similar to like an LCUE method. So there are two methods of doing this, one simple and one where you also have a discount rate and O&M cost. So if you write this in an expression, this would be, for instance, the capital cost. So we're going to say that we might have some pricing and we'll put 5 in units. We can write that inside here, but then that will give us our capex. That is the one we want to divide over the years, and then we can have the lifetime of this investment. I realize now that writing 1 year of lifetime might have been dumb, because that would be just 5, same as capex, but it could be 22 years for a cheap wind turbine. It could be 40 years for a high quality power plant. It could be so on and so forth. So if you, for instance, do a number of offshore wind turbines, they have a billions associated number with that investments, but they will last for a long time. You can annualize that cost by having this function here. That's also usually recommended for having for doing simplified in optimization, which Leap does. So that's also where it is very practical. If you want to do that a little more complex, or you have more data, you can also say that we have the CapEx, just like before. And here we have the lifetime, but here we have our discount rate. So that is called just that DR right now. So that we can apply to saying how much is our investment discounted per year. So that will be included in our annualized cost. And then what is the yearly O&M cost? So we also can put that in. That gets put on top every year of our annualized cost calculation, and then you can get some pretty realistic numbers for that. As a DEA mentioned, I should mention that these kind of data you can usually get in our technology catalogs that we use for different countries, including Indonesia, Vietnam, China, I think, Denmark, of course, and several other countries. So if you have that, you can more or less get all the data for energy producing units there, at least. So for power plants, wind turbines, on other power and heat producers, you can get that. For power consumers, we do also have some Danish catalogs where you can get this data directly, more or less, including lifetime and discount rates, everything, because this is very, very standard to look into financing. So this means also that this can be you can use this for pre-feasibility studies or larger financial changes in your energy system that your financial institutions might be very interested in, or even your banking, national banking sector. Now we've looked at the different methods for costing in the demand sector, but for the transformation and resources sectors, we actually have very different cost parameters, which are way more direct and applicable just for these sectors. So in our transformation sectors, where we generally use power plants, power producers, loss-related sectors like from crude oil to gasoline products and so on. We directly put in our capital cost, our variable O&M, fixed O&M, stranded cost if we have them in our system. So how much would if we were to not use this at all anymore, how much would our stranded cost be? And then salvage cost if we tear something down and sell it on. So some of these we can approach with annualized cost in our demand sectors, but these are way more direct and usually recommended to use for all of your transformation technology. So that's quite useful in Leap. For resources, these are the fuels. So here we have our indigenous cost, which is the cost of our fuel. We can apply that directly, both on the primary and secondary side, primary and secondary fuels. Then we can put an export benefit. How much do we earn if we do export some of our excess fuel, if we have that in our system? If we have to import, what is the cost of that? That means there can actually be a difference between domestic fuels and foreign fuels. So that is quite a big benefit to have. And then we can put in a cost of unmet requirements. That means if we cannot import and we cannot produce ourselves, we have unmet requirements, and that can be very, very costly for our system. So if we run out of gasoline in our certain country, then that will have larger economic consequences, and that we can input there. That also means that the indigenous cost, if we put that on the secondary fuels like electricity, gasoline, diesel, and so on, that also gets put on the cost of our fuel demand. So the cost that we do not put into the fuel cost we do not apply into our demand sectors directly, we put that in our resources instead, and therefore we get both. So it's very important that we also put in costing for our resource sectors. But again, they're very direct, and it's usually quite easy to find. And this is also where you have, for the future, you usually use the IEA projection data from the World Energy Outlook, which are, I think, freely available for almost anyone, and that's where I can do the projection with that. That is at least what we do in Denmark, and we do with all our partner countries. Now I wanted to talk a little bit about externality costs, because these are costed differently. So the effect, as we saw in a former video here in lesson 3, is applied to where we have the pollution happening. So that can be both in demand, transformation, and resources. That also means we cannot put the cost of the effects in a specific place. So instead, it gets its own little place in our branches up here in between key assumptions and demand. And it only works, we only get this if you have both the effects parameter on and the cost parameter on up in settings. So that's how you get this. So if that's missing, even though you have cost, it's because you haven't applied effects, and vice versa. Now, we want to add the cost to the different externalities. This is why we do that. So we do that by this method I'm showing you here. So if you right click on it and you say add, we can now choose an effect. Let's say carbon dioxide. CO2 costing is quite relevant and will be for a while. And then maybe we also want to do an effects costing on PM 2.5, because that has wider health consequences. So now we can put in our carbon dioxide costing. So that is we can do that for different things. So let's say in the current accounts, in the current scenario, we actually don't do direct costing for carbon dioxide, but we want to do that in the future in either one or all or one of our scenarios, and we can do a cost difference between that. Then these will be applied into our results. So here I'm just putting in a cost, an increase in cost of this carbon dioxide. And I think the PM 2.5, I am also going to put in an increase as we say that the value of life in the future might be higher, so we'll put in a higher cost. And of course, this you can do with just in the same way as you do anything in the demand sector. So you can both use smoothing steps, interp, or even growth rates. So you could actually quite readily link this to your GDP per capita or PPP or similar. So now I applied a few costs per metric ton or kilogram of pollution, and then we can use that in our results. So here we are going to look at the results of our costs. So now that we have put in a cost a number of different places, and also in our effects, you can see that we did that on the some places on our in our annual in our different costs. So I put in for our buses, we did a cost per passenger kilometer and so on. So now we can see, just like with most other results, we can have an avoidance costing. So we can see our social costs, that in this case, our mitigation scenario is quite a lot cheaper than our baseline. We can also go in here in cost and see we have a number of different things. Much of these relates only to transformation, but so we will look at that a little bit. So we can see we have an avoided cost in terms of our electricity generation. That's because we'll probably have an energy efficiency measures. And we can also look into more like what is our module cost balance for our electricity generation plants. So we can see that we save in our mitigation scenarios compared to our baseline scenarios. We have quite a lot of savings in terms of O&M and everywhere else because we're using new technologies. So here we can also say that we have we are looking at our fuel different costs. So we save quite a lot of money in fuels. And of course, we can go and look into that in very specific fuels. So that is what we can do do here. You can see we save a bunch of money on coal. So these are the ones in the minus. So that in our mitigation scenario, we use less money and also less fuel in terms of coal, but instead we spent quite a lot of natural gas, which is actually ending up getting more expensive, which is the total cost difference is the line we see here. So that is a real result. We can say, okay, for this mitigation scenario, we are going to spend much more money on our fuels, because we're using quite a lot of more expensive natural gas to replace the cheap coal that we otherwise use in the system. And this difference, which is I guess here, that maybe we can put to make sure that to create an equilibrium, that's where we maybe could put a certain CO2 tax or similar that will also incur this, that we can put in these that will help these policies come through.